In this lesson, we're going to take a brief look at some trigonometric functions and how we can apply the ideas of calculus to these ones that involve the word sine, cos, tan, things like that. So just to throw them out there, some basic ideas. Instead of developing them this time, I'll just tell you. If you have a function with sine in it, the derivative of sine is cos. And similarly, if you have a function with cos in it, the derivative is sine, except for here, be careful, it's the negative of sine. Okay, so lots of things involving sine and cos. They're sort of more complicated, so that's where we use the chain rule lots of times. So in this little example that we have here, for the sine of some sort of function, well, the derivative of sine gives you cos. So you take your cos of your original function, and then you have to times it by the derivative of the interior function. That would be this piece right here. Yeah, it's just some real basic introduction here to trigonometric functions. So let's take some derivatives. I want to find the derivative of sine of 2x. Well, my derivative is the derivative of sine becomes a cos of the function, and the function is 2x. That's its own little piece there, times the derivative of the interior function. So what's the derivative of 2x? Well, that's a 2. So a better way of writing this would be 2 cos 2x. You can try the next one. So the derivative of my function would be, I got a cos in there. Derivative of cos is a negative sign. So the derivative of this piece would be 2 negative sine of the original function times the derivative of that function itself, of this piece, which is 3. So notice that the constant at the front is still there. The cos became a negative sign. I just put the negative out front just to make it a little bit easier. Okay, and then we're going to rearrange this. We'll multiply this times that, which gives us negative 6 sine 3x. I like to put in brackets just to identify that part and piece for myself. All right, I'll try some more. Hey, I've got a bunch of different functions involved here. So the derivative of x squared, well, that's 2x. The derivative of cos x, that's a minus sine. And the derivative of sine pi over 2, almost like a trick question here. The sine of pi over 2 is not a function. It's a number. Sine of pi over 2, or sine of 90, punch in your calculator, and you get a number. You get the number 1. So what's the derivative of number? Always a constant? Nothing. So our derivative of this function is just that. Okay, let's try the next one. Y equals sine squared x. Well, if you think about it, that really means sine x squared. That's a power rule question. What do we do with powers? We bring them down in front. We time them by the original one, but we subtract 1 from our exponent. And then we multiply that by the derivative of the inside piece. The derivative of sine x is cos x. So the way you'll often see this written is just 2 sine x cos x. Okay, but we can apply all those other rules we've learned back in the past, power rule, quotient rule, chain rule, all those things can be applied to trigonometric things just as they can for exponential. Okay, we got a product this time. My derivative of the first piece is 2x times the entire second. My derivative of the second piece is cos x times the entire first, just like it did in the old days. Okay, we often rewrite this with the x parts first. Okay, just to make it a little bit confusing, so it's not the cos of x squared or x cubed or something like that. Okay, if you really wanted to, you could even common factor that and take an x out of both parts. All right, let's try a tricky one. The derivative of sine of cos 3x. So when we go to do this one, let's move it down a little bit here so we can talk about it. This is my function of another function, kind of like the composite function, if you will. So my derivative will be, well, the derivative of sine is cos of the original function. My derivative of the gx part, which is cos 3x, is the negative sine of 3x. And I gotta be careful here because really it's not g at x, It's g at h of x. Oops, I need an x in there. There's a function inside its own function there. So I need to multiply the end of this. What's the derivative of the 3x part? That's 3. Okay, so the way we write this one, so we have to put the number out front, so 3, and then the cos of cos 3x times, oh, I have a negative sign there too, so I'll put at the front also, sine 3x. And that's a pretty messy one. Lots of parts and pieces to keep track of there. In particular, functions inside functions. They're kind of nested inside each other. All right, try a couple more. Oh, we got ourselves a quotient, a fraction. We know how to deal with fractions. What do? Take the derivative of the top, which is cos x, times the entire bottom, minus the derivative of the bottom. So derivative of 1 is nothing, so don't worry about that part. But the derivative of cos x is negative sine x times the entire top. And we put that all over the bottom squared. And then we start simplifying this. So let's try that. On top, we're going to get cos x plus cos squared x. And the right side, we have a negative times sine, which just gives us positive sine squared. And we got on the bottom 1 plus cos x squared. Now, are you ready for this? Here's where identities from grade 11 come in handy. You might, I hope, recall there's an identity of sine squared plus cos squared equals 1. That's one of our basic identities. And I hope you see that in this question right there. Because I'm going to simplify by using that. Now on the bottom, just to make life a little bit easier, take a look what I can do here. I hope you agree that these two things are still the same. I just changed the order. And why would I want to do that? Well, if I have things that are the same on the top and the bottom, I can cancel them. In other words, I can cancel one whole thing of these with one of these. And I'll be left with 1 over cos x plus 1 as my derivative function. Okay, so those identities we worked on last year are going to come back to haunt you a little bit now. Okay, just some of the basic ones. Speaking of which, that leads us to tan. Now tan is not something I've given you a derivative for, but we know that tan actually means sine x over cos x. Again, an identity. So if I want to take my derivative for this one, the derivative of sine on top is cos times the entire bottom, minus the derivative of the bottom, which is negative sine times the entire top, all over the bottom, which is cos squared. What can we do on top? Well, we can simplify cos squared plus sine squared. The bottom is just cos squared. And what is cos squared plus sine squared? Well, that's one of our identities we just talked about. That's 1 over cos squared, which, if you remember, is related to a reciprocal identity. You may remember the idea of a secant being 1 over cos. Or if I square it, then I square it. So the derivative for tan x is actually secant squared. Okay, so we don't actually have to define identities for all our functions. We can calculate them using ones with sines and coses and quotients and products and all kinds of stuff. But as I just said, and I'll give you a third one. So now we have 3, sine, cos, and tan. We can figure out their derivatives pretty quickly. Okay, so let's take tan, its identity, and use it to figure out some more derivatives. So I want the derivative of tan 3x squared minus 5. The derivative of tan is secant squared of the function. And the function itself, remember this is its own function inside, has a derivative of 6x. In other words, 6x secant squared of 3x squared minus 5. And so as you can see, trig functions get pretty messy when you start taking derivatives of them. because a trig function is constantly changing, right? And so its derivative has to be constantly changing. Yeah, try the next one. Y equals tan x. Well, the derivative of tan x is secant squared. So if I think of this as f and g, derivative of f is secant squared times g plus derivative of g, which would be cos x, times the original one. Now, nothing wrong with that, but we often will change things by simplifying using identities. Hopefully remember that tan is really sine over cos. So you're often going to see this function, derivative, as something looking like this. Because we can cancel our coses. And again, if you wanted to, you could even common factor this and say to yourself, well, this is the same as just sine x and secant squared x plus 1. And down the road for solving something, that might be handy, right? Being able to factor things. Okay, last two. Let's try tan x minus sine x cubed. That looks like a power rule idea, which means my exponent can come down in front, times the derivative, sorry, times the entire original thing, let's subtract 1 from the exponent, times the derivative of the inside. Well, the derivative of tan is secant squared, and the derivative of minus sine would be minus cos. Now you're probably going to ask, can I go any further with that one? And this one you can't. That's as far as you can go with that. And if we try the last one, tan cubed x, which just really means tan x cubed, means our derivative will be 3 times tan x squared times the derivative of that, which is secant squared. And again, can't really go any further. I think what identities, tan would be sine over cos. Secant is 1 over cos. So no coses will cancel. You might as well stop there. Okay, so we can take derivatives, just like we always have. Okay, we can use those to create new identities and new derivatives of other functions. And we've gone through sine, cos, and tan. We talked about secant. Well, we can also talk about the other two, cosecant, cotangent, things like that. Okay, and we can take and find their derivatives by using those reciprocal identities. I'm hoping that you remember that sine x is 1 over cosecant. And as we said, that cos is 1 over secant. And you're hoping, remember, these are also interchangeable. So just like cos is 1 over secant, secant is 1 over cos. And vice versa back up here for sine and cosecant. Now our little trick we talked about was s goes with c and c goes with s when you think about which reciprocals go together. So using those, we can actually find derivatives of some reciprocal functions. I want to find the derivative of cosecant. Well, what does that really mean? Cosecant really means 1 over sine. How can I find the derivative of that? Well, if you will, our derivative, you can think of this as either a quotient function, or we can think of this as sine x to the negative 1. That's the same thing, right? That might be easier in this case. Bring our exponent down, subtract 1, so we're negative 2 now, and the derivative of sine x, well, that's just cos x. So the derivative for cosecant is really negative cos over sine squared. And I got sine squared because I'm bringing my negative exponent back to the bottom, right? This piece ended up back down here. So there's an expression for that one. Can we do the same thing for secant? Of course we can. So if I want to do y equals for secant, actually let's fix that, sorry. Y equals secant is the same as 1 over cos, which, I'm just going to get rid of this stuff over here, sorry. It's like saying cos x to the negative 1. So when I go to do my derivative now, I get negative 1 cos x to the negative 2, and the derivative of cos x is negative sine x. So we end up with 2 negatives make a positive, sine x over cos squared x. Okay, and that's our first lesson, just taking some derivatives of these kinds of functions involving sine, cos, tan, secant, cosecant. And you can do the cotangent too. We didn't do it here. I think that's actually in your homework, one of the questions, to give it a try. Here's your homework. Give them a try. Again, they're just derivatives, making sure we can do the different types and pieces. And then we'll put them together into tomorrow's lessons and how we can apply them a little bit.